All right, y'all. Welcome to week 4. So, glad to have you all as always. Feel like we're getting smaller. Don't know what that means, but glad you're here. As usual, quick logistics update. Quiz 3. Quiz 3 is this week on electric potential and potential energy. So, as always, make sure you're doing those problem set problems. I heard a couple concerns about the discussion sections. They still hadn't shown the solutions. I've reached out again. So please let me know if that doesn't happen, and maybe I have to do more severe measures. We'll find out, but hopefully they should be doing the solutions with you all this week. If not, then yeah, we have a big problem. So this will be the 3rd time I've kind of reached out to them about that. Sometime this week, I will do the transferring over of the discussion grades and also the iClicker grades are all there. The discussion grades, and I will take your quiz grades and move them to the adjusted columns. Reminder, the quizzes, when you take them, are 5 questions, and it grades them out of 5 points. But the reality is I'm going to grade them out of 4.5 points. And to make that shift, I have to do it manually, so that's why it hasn't happened yet. So I'll go ahead and do quiz 1, quiz 2, move those over to the shifted ones. I have to decide whether or not to put your financial aid activity either there or in homeworks. I'll probably put it in the quizzes because it'll boost rates a little bit more, I think. So there's that. Reminder to you all, we are at the end of January. February 16th is our first test. I have diligently been putting together your test for this class. I think I've ultimately, as I get closer and closer, I refine the details, I believe I've ultimately landed on a 60%, 40% split. I'll probably send out an email with these exact details, meaning 60% of the points will be the multiple choice, and the other 40% will be the free response. There will be somewhere between 20 to 25 multiple choice questions. That number hasn't been decided yet because I need to time it. The way I'm going to determine how much questions to give you all is I will take it myself. And depending on how much time it takes me, I will multiply that by 3, and that'll give me a good indicator of how long it will take you all. We'll see if that's accurate or not. So that'll determine between the 20 and 25 questions, and then for the free response, it will be 3 questions, but you only have to do 2 of them. You will get to choose which 2, so that'll let you kind of choose the ones that you feel the most comfortable with, and those will be graded on partial credit. The multiple choice is all or nothing. Either you get it right or you get it wrong. That's why I want to ask enough questions so that if you miss one, it doesn't hurt your grade too much. But I don't want to give so many that you don't have time to double check your work. Free response, that's going to be graded on partial credit. Again, I will send all this out, but the partial credit will be graded based on the steps that we've been talking about. So step 0, did you draw a picture that's accurate? Step 1, did you write down the givens accurately? Step 2, did you identify what you're missing? Step 3, did you identify the right equations? Step 4, did you plug them in correctly? And then at the end of the day, if you get the answer right, you just get all the points. The partial credit doesn't really matter. You just get all the points if you did everything right. The partial credit is if you get the final answer wrong. It's so we can still give you some points for showing your knowledge, because at the end of the day, that's the purpose of a test, to show how much you understand. So, the partial credit, again, if you get it right, done. Even if you show no work, you'll get the full points. If you get it wrong, we'll start looking at that partial credit and award points accordingly. I'll send out that exact kind of rubric for how that'll be scored, just so when you do the test, you can make certain to show the right things. But it's going to be the stuff I've been talking to you about so far. I will give you all, I told you all about those 5x8 note cards. I will probably bring those in this next Tuesday. The following Tuesday, the 14th, is when we will go through that note card together. So on the 14th, part of the class will be spent where I will give you an example. I will size my PowerPoint to the size of a postcard, and I will literally say, here is the note card I would make. Here are the key things you're going to want to have on it. There will end up being some extra space at the end so that you can put whatever extra you want. You can do anything to your note card you want as long as it's one note card. You cannot staple multiple pieces of paper to it because then it's not one note card, but you can like print out something and then glue it to it. That's fine. The amount of writing you can fit in the front and back of a 5x8 note card is what you're allowed to bring. Okay, so that review will happen on the 14th. We'll also maybe do some practice problems. I may send out a survey and say which problems have been the most challenging, and those are the ones I'll focus on. That'll happen sometime next week. But just want to get you all prepared for that, get you in the mindset that that is coming up. Remember, if you are doing well on the quizzes, I expect you to do well on the tests. So if you're monitoring, hey, how do I expect to be doing? If you're getting 4s or 5s on the quizzes, I expect you'll do well on the test. If you are getting 3s, you're going to maybe want to review some of those older concepts, really, like maybe even just redo. You won't be able to get the points for it, but like pretend like you're doing the quiz again from scratch and see if you can get that 5 out of 5 or that 4 out of 5. Also, last reminder last logistics thing before we get going. Every Tuesday after the quiz is when I will post the solutions to that quiz. So today I posted the solutions to quiz 2, so if at any point there was a problem that you were confused about and you did not know how to solve it, every Tuesday I will post the solutions under that week. So last week was quiz 2, and you can see here I posted the solutions to quiz 2 as well. So just for your all's knowledge, if there was a problem you're stumped on, that's when it'll get posted. Why Tuesday? It gives me time if I have students that have an excused absence for, there's that list of excused absences. It allows me to give them a couple extra days for the quiz based on that absence. So, yes, sir.
Are you going to post a solution or the process?
Both. So if I open this up, when I do the quiz solutions, because this is something I tested you on, it's fully written out in detail how to solve it. I don't do it for the problem sets just because, 1, there's a bunch of them, and 2, I want to encourage you all to solve it out. And if I put the full worked out solutions, it can lend people to a false sense of security that they know how to do it by just looking at my solutions, and also want to encourage people reaching out to tutors and things of that nature. But for the quiz 2 solutions, that's done. So I do the full board. Here's how you do it. You all will have, I mentioned this before, your quiz there's multiple versions of each problem where I just change one tiny detail. Like I change one of the numbers or things like that. So the problems here may not be identical numerically to yours, but the process is identical, just kind of change the numbers with the ones that you have. Ultimately, the reason I post these is so you can understand the process and you can apply that to your problem and see what the right answer should have been if you had a different version. At any point, if you're doing that and you're stumped, please, of course, reach out to me. Okay. Any quick logistics questions about tests, quizzes, discussion sections, whatever, before I move on? Awesome. Okay, so last class we talked about voltage. We talked about electric potential. We finished electric potential energy. I want to spend a few more moments on it. I'm going to solve one problem on it as well. Voltage, potential energy, potential difference. The problems for this are honestly mathematically easier than electric fields and forces. So there's no vectors, so there's no breaking things into components, nothing like that. But the concepts are more confusing. What is voltage? What is potential energy? Those are usually a little trickier to understand, and there's usually some mix-ups that end up happening. So I want to spend just a few more moments on it, remind us what the heck we covered, remind us of the differences. So straight off the bat, I want to remind us that we kind of introduced a whole bunch of words, and I wanted to distinguish the differences between them. So electric potential energy, the key word there is energy. And what the reason I'm emphasizing this is one of the most classic mistakes that people make when they're solving problems in this section is they see electric potential energy and they think electric potential. Or they see electric potential and they think electric potential energy. The key word there is energy, and if you see electric potential energy, the variable is U. U, that stands for potential energy with a little E next to it for electric potential. Reminder to you that electric potential energy equals Q times V. Well, what is V? That is voltage, electric potential difference. Those are 3 words three phrases that all mean V, variable V, voltage. Remember, this voltage is the potential to have energy. You can have a potential and have no energy. Just like I can have a height and have no energy, things only get an energy when I put something with mass there. The same thing with voltage. I can have a voltage, but I have 0 energy until I put a charge at that voltage. You do not get energy until you put a charge at that voltage, just like you don't get a gravitational energy until you put a mass there. So I want to make certain that you all have those two things. They're connected, but they're two separate things, and please make certain you're using the right one to solve your problem. Other thing I want to point out here is that whenever we're talking about electric potential, there is implicitly a difference there. So that may sound a little weird. There's always, just remind you that triangle there is delta, which says difference. There is always a final and an initial. Whenever we talk about voltage, you have to have a reference to, just like height. I mentioned that to you all previously. Whenever we say how high something is, every time you tell someone how high something is, you are referring that height with reference to something else, the ground generally. When you're talking about how high up something is, you're always referring to something generally, we call it like how high the ground is. But even if we just think of this class, you can see the ground can be defined, honestly, an infinite number of ways. I could define the ground as my distance from me to this floor right here. So from my perspective, how high up am I? 0. I have 0 height, I'm on the floor. From your all's perspective, my height is about 1.5 meters. Because you define me, the ground is down there. If you're in the back of the room, you're probably actually the same height as me. So even when we talk about height, there's an implicit difference involved. There is somewhere you have to define as 0. When we talk about electric potential, that is also true. If we're talking about charges, that 0 is at infinity. So at infinity, so if we have a charge, and I say, the potential, I'm calculating the potential somewhere, KQ over R. Even that, when I'm calculating V there, that is technically a difference. Where is my 0? Infinitely far away from it. So when I'm calculating this voltage, I'm calculating the difference in voltage between this point, which is a distance R, and a distance R infinitely away. So even this, there is a difference, but it's kind of hidden and you can't kind of see it. So this is a very important concept to understand that whenever you talk about voltage, there's a difference involved. And when we start talking about current, when we start talking about batteries, when we start talking about circuits, it's going to come in a lot there. And so voltage is probably the most useful thing I'm going to teach you all, just because it's something, an easy way to prove that is something you actually have heard about before, batteries, power outlets, things like that. An example of this that's actually pretty interesting is if you have a downed power line, you can be standing right next to that power line and it's down and you're okay. When does it become dangerous? When you take a step and you have a gap. So now with the power line here, 1 foot's here, 1 foot's here, I've introduced a difference in voltage. The foot that's closer to that down power line, there's a high voltage here, there's a low voltage here, that electricity can run through your body, and then we'll learn about voltage, we'll learn about current there. And that's when it becomes dangerous. But if you're standing perfectly still, you're fine. Same thing with like power lines. If you're connected to the same power line, you're okay, but the second you touch something else, you get that difference, and that's when things matter. Other key thing here that I emphasized last time, everything wants to go to lower potential energy. Everything wants to go to lower potential energy, but I told you all that when we talk about just potential, aka voltage, charges go from high potential to low potential, and negative charges go from low potential to high potential. Notice I did not use the word energy in those two small bullet points there. They both are going to lower potential energy. But I'm not talking about potential energy here, I'm talking about potential. And we saw that before, and I calculated it out, and I proved to you that, and you can look back at that before, that negative charges are going to lower energy, because when we multiply a negative times a big number, we get a small number. A big negative number is a small number. So, if you want to check that out previously and kind of see why that's true, that was in the previous slides, the 2 clicker questions in particular. Alright, and I slightly moved my laptop and it's angry. Alright, so we're going to go ahead and do a problem. This problem is number 2 in the practice set, and it mentions voltage, and it is a potential energy problem, or a conservation of energy problem. Fingers crossed that all is well in the world, and I didn't just ruin all my hopes. So I'll just start reading it as I slowly unplug and plug things in and finagle the wires so that the contact is good. So the problem says I have an evacuated tube that uses an accelerating voltage of 44 kilovolts to accelerate electrons to hit a copper plate and produce X-rays. Ignoring relativistic effects, what would the maximum speed of these electrons be? Alright, so let's draw a picture. We have some voltage, so we have some plate that they're going to hit. They're probably going to start over here. They're a negative charge. They're an electron. And they start here, and between these 2 points, there is an accelerating voltage of 44 kilovolts. This is where we can already start to get that idea. Reminder that whenever I talk about voltage, there's always an implicit difference involved. So, if there's an accelerating voltage of 44 kilovolts, we can actually use that rule that we talked about before. I want to give you all a few seconds. Where should the higher voltage be? I will tell you it's a difference. So one side will be 44,000 volts. We'll just make the other side 0 to make our math easier. See if you can determine which one should be 44,000, which one should be 0. Does it go from low to high voltage or high to low? Give you a few seconds to think about that. Let's jump back to that previous slide. If we look at the negative charges go from low potential to high potential. So, which one's smaller? 0 is smaller. So let's say this side is 0. Let's say this side is 44 kilovolts, which is 44 e to the 3, 44,000 volts. Remember, anytime I talk about voltage, there's an implicit difference involved. Assign somewhere to be 0, assign something else to be that 44,000, this is the reason it moves. If both sides were 44,000, it wouldn't move. In the same way that my coffee cup on this table is not moving right now, because everywhere on this coffee table is the same height, and things do not move if they're at the same height. You need a difference. If I lifted up one of these tables and made one of the ends higher and lower, then it would move. Then I have a difference in height, and things move down the slope. So, we got our setup here. We have an electron. If we want, well, we'll do step 1. We'll put that information there. So step 1, what's given? Well, we have an electron, and we've probably gotten pretty good at this point of realizing when there's an electron, we need the charge of an electron, which is our negative 1.6 times 10 to the minus 19 coulombs. And I should say this now. There's a key word in this problem that tells us how to solve it. Before we do anything in the problem, there was a hint I gave you all that if you see this word, speed, there's a way that you should solve this problem. If you see the word speed, there's a way to solve this problem. So I'll give you a few seconds, see if you can remember. There's a technique, if you see the word speed in our class, at least leading up to the first test, there's a technique we're going to use. See if you can remember. It is conservation of energy. If you see the word speed or velocity in any problem I give you, you will be using conservation of energy. So, the reason I mention that is we're going to find out that we're going to need the mass of an electron, which I'm fairly confident is 9.11 times 10 to the minus 31 kilograms. But as with all things, it's better to double check. Especially because I haven't used that too much, so I don't know off the top of my head. So handy Google, we will add this to our nice little note card. So Google says that the mass of an electron is 9.109 times 10 to the minus 31. I'll go ahead and round that, and we're good to go. Great, so that's the mass of an electron. I was right. What else is given? We have our voltage initial as 0. We start at 0. And our voltage final as 44 e to the 3 volts. Okay, and that's pretty good. That's probably going to be everything we need. You all probably noticed I'm fairly decent at knowing all the givens we need, but reminder to you all, as you're solving a problem, if at any point you're like, I feel like I need this variable, you may go back to step 1 and add that too. You may realize, I need this additionally. Maybe you get to step 3 and realize, it's conservation of energy, I should put the mass. Go ahead and just kind of put that back there. I have done these problems, so I know what information I need. But if you ever feel like for example, nowhere in this problem did it use the word mass. So you may have needed to get to the step where you realize, it's conservation of energy. And then you go and say, okay, I need to add mass to my list. So what are we solving for? We're solving for the maximum speed. We'll go ahead and use v for velocity instead. And we're going to use conservation of energy, as mentioned previously, because we're solving for speed. We're solving for velocity. Conservation of energy says that the potential energy initial plus the kinetic energy initial equals the potential energy final plus the kinetic energy final. Okay? And we can remind ourselves that potential energy is equal to Q times V, and that kinetic energy is 1/2 mv squared. So that when we plug those in, we can put those in instead. So that's our setup. We've done all the hard work. At this point, it's plug and chug. Honestly, if you get to this step on the test and you've done all these steps correctly, and you plug everything in, you will get most of the points for that problem. You will have shown me that you understand how to do it. I will not knock a ton of points off for any kind of algebra mistake. Certainly, if when we get to step 4, you plug everything in and the only mistake you make is a calculator error, you will get, I don't know how many of the points, somewhere above 90% of the points for that problem, or probably like 95%. You'll lose very few points if you set up everything correctly and you just fudge a number when you plug it into a calculator. Yeah?
Is that for multiple choice as well?
Multiple choice is all or nothing, but multiple choice, the beauty of it is, if you fudge a number, like you accidentally hit the wrong number when you plug it in, your answer won't look like any of mine.
Sure.
My answers are that I give on the multiple choice. You will only get them if you do it right, or if you blatantly do it wrong. Maybe you accidentally square it when you weren't supposed to, or you didn't square it when you were supposed to. There is answers in the multiple choice that will line up if you accidentally make some of the common mistakes that I've been harping on. Yeah, it's a good question. All right, let me go ahead and make a new slide, copy all this over. We'll do step 4, plug and chug. Maybe the most satisfying one, because at this point you've done all the hard work and it's just putting all the circle pegs in the circle holes. All right. So, have our nice picture. So step 4, let's plug in our things. So, I'm going to go ahead and just rewrite it first. QV initial plus 1/2 MV initial. I always write more up here than you are welcome to write as many steps as I do, but I always write more than less just because I want you to make certain you're catching every step. You'll notice that in my solutions as well, I try to write more steps than less. At this point, we start plugging in. To make my life a little easier before I start plugging it in, let's see if we can cancel. Oh, and this is, be careful here. I just realized this may be a small mistake you all make. We have capital V's and we have lowercase v's. When you plug in stuff, make certain you don't make that silly mistake. I could totally see that happening. One thing I recommend doing that I didn't actually do a good job here is when you write lowercase v's, I recommend putting a little kind of lip on it, and that'll be a way to distinguish between the two, because otherwise a capital V and a lowercase v look identical except in scale. So whatever. Put a little lip on it. You'll notice I do that on some, should do it a bit more, but we'll notice that we can cancel some of these terms right off the bat. For example, my initial voltage is 0, so bam, that term goes away. That's 0. Pow, gone. This term is 0. Why? Because V initial is 0. My initial velocity is also 0. You know, I was talking all big and bad before and saying, wow, Dr. James up here, he always puts all the right givens in. But actually, I didn't put one of the givens in here. And I actually could have done a better job. We were solving for the final velocity. So our initial velocity, I didn't put here, and we could have put that, is 0. We do kind of need to know that information. Why? Because it's not moving. My thing starts not moving, and then it starts moving. It says it accelerates a thing, an object. If you're ever accelerating something in this case, assume that it starts from rest. If it does not specify, assume my object starts from rest. So bam, this term also equals 0. And here's where you're going to get something weird. You're like, one side is 0. I start with 0 energy? How does that make sense? Because that means my final energy is 0. Well, let's go ahead and do the math, and we'll talk through how that makes sense in a second. So that whole side is just 0. That whole side is just 0. So let's go ahead and put our Q in here. Our Q is a negative value, and this is maybe where it'll all start to make sense. Our voltage is a positive, and that's a plus 1/2, 9.11 e to the minus 31. What a tiny, tiny number times Vf squared. And we can already look at this, and if we're careful, we can realize how it works out. We are adding a positive and a negative number, and so they will cancel to 0. And so then we can kind of pause here and think, how do you have 0 energy? Energy is relative. What does it mean to have zero? Energy, kind of like height, is all relative. You can only kind of compare it to something else. So when we're doing conservation of energy, starting with 100 joules and ending with 100 joules is effectively the same as starting with 0 and ending with 0. What's important is that they're the same before and after. But energy is all a relative idea. Because what are we comparing energy to? What does it mean to have a bunch of energy? You have to compare it to something. And so you can get to some all sorts of interesting stuff there. So at this point, it's kind of plug and chug. I'm going to go ahead and do the algebra. I like to get everything in terms of VF by itself before I plug it in. The less times you plug things into a calculator, the less likely you are to fat finger the wrong number and make a mistake. So we'll go ahead and add this side over. So we're going to add that negative 1.6 times that. We're going to add that over. Again, I'll show more steps and less. I'll be kind. So 1.6 e to the minus 19 times 44 e to the 3 equals 1/2 times that 9.11. This is where one of the benefits can be of leaving things in terms of variables as long as possible. In our case, we put in the number sooner. That's fine. We just have to write a heck of a lot more. Yeah?
So 44 e to the 3?
Yes.
Should that be negative?
So it was positive because if we look at our picture up here, we said it was a 44 kilovolt potential difference. So we said, okay, what do electrons do? Electrons move from low voltage to high voltage. So we said our initial was 0, and it's going to move to a positive 44 kilovolts. So because that the potential difference it gave us was positive, and we had to decide, does it start at 44 kilovolts and end at 0, or does it start at 0 and end at 44? In our case, we decided it ended, which meant our final voltage right here is 44 e to the 3. This is the positive, so when we plug it in, it should be a positive.
Yeah, but when you move it.
When we move it, that's a great question. Our charge was negative. So right here, this was a negative times a positive, so that'll be a negative. So when I add that, I get rid of the negative. If you have a negative on one side, you can get rid of it by adding it to the other side. And that'll get rid of my negative side. Easy example, if I have like x equals negative 3 plus y, I can say x plus 3 equals y. I can add that 3 over to the other side. Anyway, I'll let you, we can talk more about that. If we had set it up, if I'd kind of multiplied this out, I could have made it a subtraction. You would have seen it would have been addition. Yeah, we can talk more about that. That's just an algebra thing. So at this point then, I ran out of room because I wrote more than less. This is why sometimes writing things in terms of variables to the very, very last step. So like I could have solved for VF in terms of all these. I put in the numbers because I think that's traditionally what we may be more used to. So hope that would make it more clear. So VF is going to equal, I multiply the 2 over, I divide by the 9.1. So VF squared is going to equal 1.6 e to the minus 19. And at this point, it's just the slog. We multiplied by a 2 to get that 1/2 gone. We divided by the 9.11, e to the minus 31. And this is where, just when you're doing the algebra, be careful. You will get docked some points if your algebra is off. So when I mentioned, like, you will lose very few. You still won't lose many points, but you will lose more than just if at the end of the day, this is on your paper. 1.6 times 10 to the minus 19 times 44 e to the 3 divided by 9.11 e to the minus 31. If this is on your paper and literally the next step you just have the wrong number, you'll lose very few points. Very few points, because I'm testing you. Yes, ideally we're all decent with a calculator, but at the end of the day I care more about, can you solve these problems, can you rearrange it. So let's see if we get what answer we get. Let's see how fast this thing is going, if it's a reasonable number or not. Thank goodness we got a square. We're dividing by a very, very small number. So we should expect to get a very big number, but we have a small number on top. Woo! All right. It's a big, big number. I remember doing this problem last year, and I actually think I had to adjust the numbers because I had it going faster than the speed of light, which is not ideal. If you remember, I hope they taught you this in Physics 1. If not, I'll teach you it now. Speed of light is the speed limit of the universe. It's 3 e to the 8. This problem actually gets so close to the speed of light, technically we would have to know general relativity to account for it, but whatever, obviously you don't need to know that for this class. Fun fact, as you get closer to the speed of light, it gets harder to go faster. Your mass actually effectively increases, that's why it gets harder, and as you get closer to the speed of light, your mass approaches infinite. Fun things, world is weird. There's your answer, 1.24 times 10 to the 8 meters per second, so yeah, up almost half the speed of light. It's very fast. It shows you how strong 44 kilovolts is. That is enough to make one single electron move very quickly. So, we did all this math. Honestly, most of my space was just devoted to the algebra. The setup was actually fairly short, and at the end of the day, it may look more intimidating because I wrote out all these algebra steps, but how do you solve this problem? You recognize its conservation of energy, you recognize that voltage means that there's a difference, and you assign the voltage to the right places. Electrons go from low voltage to high voltage, and so we need to do so accordingly. If you notice here, a good point here, just to remind you all that it moved to lower energy, it started at 0 potential energy and went to a really big negative potential energy. A big negative number is a small number. Negative 1,000,000 is a very small number. It's a much smaller number than 0. So, there we go. There's a quick recap. Hopefully that helps clarify some points. Maybe so, maybe not. Yeah.
So if it was asking for protons, that's when you would start at the higher number?
Yes, that's a great question to ask and a really good counterexample. If this was a proton instead, this would be 44 kilovolts and this would be 0. The voltages would flip, but my sign of my charge would also flip. So it would still work out mathematically. The sign of the charge would flip, but so would your voltages, so it all kind of Stevens itself out. Any other questions on this? Again, I know voltage is weird. All right. At any point, if you all have questions, please email me. Again, I will respond within 24 hours, exempting weekends. All right, so let's go ahead and start talking about capacitors and resistors. I was okay with spending more time on this voltage stuff because honestly, the next 2 weeks of content is not bad. This week we have an okay amount to get through. Next week we don't actually have that much to get through. If you see the slides, they're like very short. We'll probably be able to get them covered in 1 week or in 1 day out of the 2, and then we'll just do a bunch of practice problems additionally. Capacitors and resistors, we are starting to get into electricity. And by electricity, I mean the stuff you're familiar with, the stuff that comes out of the wall. Capacitors and resistors are 2 things that can be in a circuit. You may have heard the word resistors, you may not have heard the word capacitors, but as usual, we're going to start from our understanding of the concepts we've covered, and we're going to kind of build a capacitor. We're going to build this capacitor from scratch. So, what's our goals? We need to identify what a capacitor is and its function. We got to learn some terms like capacitance, and based on these capacitors, how much voltage they have, charge, and the energy stored on it. Then when we get to resistors, we need to define what those are, what's their function, this thing called resistivity, and how to actually calculate the resistance given a bunch of different parameters. Why is this stuff useful? Because these things are immense. Every single electronic device you have has resistors in it and capacitors in it. Your phone has capacitors in it, and literally anything that electricity runs through has a resistance. The wire every single wire even has a resistance, and that's the simplest thing in a circuit. So, these are fundamental pieces of a circuit, especially resistance. Capacitors are very, very important. I'll give some big examples. The more common uses are a little trickier to describe, but they're there. Alright, so here's a picture of a capacitor. We're going to explore how to build one as we go on, but this will kind of preview it. It's a parallel plate, and we have seen parallel plates. We've seen the electric field due to parallel plates. That's where we're going to start. And I just want to show you in reality, you're never going to find a capacitor that's 2 giant parallel plates. How do you actually make capacitors? They're all cylinders, because if you take these parallel plates, you put some insulator between it, and you roll it up, it's effectively the exact same thing. So being efficient with the space, whatever. You don't need to know that. But when you see a capacitor in a circuit, if you ever see something in a circuit that literally just looks like a tube, a cylinder with some things poking out of it, that's a capacitor. Anytime you all see a circuit board and you see some cylinders on it, that's a capacitor. Alright, yeah, so here's some of those examples. StepFinder uses capacitance, your touchscreen uses capacitance. If you use a car amplifier, you can use a capacitor to make certain when the base is going that it can have enough volts current. Lightning, kind of, sort of. Defibrillators, that's probably the most common one for those medically related. So on and so forth. Capacitors, we're going to learn their main role is they're basically a glorified place to store charge. You could think of it like a cup stores water, a capacitor stores charge. If you need a heck of a lot of charge in a quick moment, you use a capacitor. That's the purpose of it. So, in the case of defibrillator, you need a heck of a lot of voltage, a heck of a lot of charge. Bodies are fairly resistive. You need to pump some current through it. Let's get it. Yes, there's some more pictures of them. Great. Let's actually start just developing it. Let's see if you all remember the equation for if we have one infinite plane. We've seen some pictures that a capacitor is two infinite planes. So let's build the equation for the electric field inside a capacitor. And honestly, you all saw this for the discussion question, so this may start to seem familiar to you. That was one of the reasons for giving that discussion question, was to kind of prepare you from when we got to this point. Discussion points are free, so there was no kind of harm to it. What is the equation for the electric field due to an infinite plane at a distance r away? Is it sigma, which is charge density, over 4 pi epsilon naught r squared? Is it capital Q, the charge stored on it, divided by 4 pi epsilon naught times r squared? Is it sigma, charge density, over 2 epsilon naught? Or is it sigma over epsilon naught? What is the electric field at this point P due to an infinite plane of, in this case it's positive, but it really doesn't matter. We'll say positive charge. What is the equation for that? This will be one that we will certainly put on our formula sheet. We're going to put all the equations due to, we had a line of charge, we had a plane of charge, we had a sphere of charge. The plane of charge, though, was the most useful one because we're using it today. It's going to be used in capacitors. All right, we'll go to 25. If anyone's still rummaging through their notes for this. 5, 4, 3, 2, 1. All right. So it's looking pretty good. Spot on. Remember that infinite planes had the really, really interesting property that their electric field did not depend upon distance. The electric field nowhere in this equation is d or r or x or y or z or any of those variables that we associate with distance. This sigma here, just to remind you all, was the charge over the area of the plate. So however big that plate is, you take the net charge, you divide it by the area of that plate. 2 is 2, epsilon naught is 8.854 times 10 to the minus 11, minus 12. It is just a constant. It is not dependent upon distance. It's just a number. So that was our equation. So building on that, and again we saw this with our discussion problem. Building on that, let's put 2 plates. And what is the equation, do you think, for the electric field at a distance r? Instead of having one infinite plane, I have 2. And this point does not matter where it's located. It could be really, that's my hint to you. This point could be over here. This point could be over here. This point could be over here. We just saw that for one infinite plane, distance didn't matter. Well, shock and awe, 2 planes, it still doesn't matter. The distance does not matter. Where you are located does not matter. The electric field is constant between these two. What is the equation for it? I have, instead of one plane, I have 2 of them. So that's kind of my hint to you. Both have equal charge on them. Both are equally sized. Both are identical in every way, but the one on the left is positive, the one on the right is negative. So this one has positive capital Q, and this one has negative capital Q. Exact same areas on those planes. They're identical in every other way. All right, we'll go to 130. So 5, 4, 3, 2, 1. All right, seeing some differences here, and that's okay. I'm basically asking you to derive one of the equations we're going to use here. It is D, and it's going to be, we're going to show you why. If it doesn't make sense, hopefully by the end of this explanation it does. Remember, whenever we're finding the net electric field, we consider one system at a time, whether that's one point charge, or in this case, one plane. So we pretend like this plane over here doesn't exist, and we say, what is the direction of the electric field at this point R due to that positive plane? Well, we remember that the electric field points away from positive charges. The electric field points away from positive charges. Okay? Then we do the exact same thing for the negative charge. We pretend like this one doesn't exist, and we say, at this point, which way is the electric field going to point? And we remember that electric fields point towards negative charges. And now we just write down our equations. We want to find the net electric field. That's going to equal E1 plus E2. Well, we remember from that last slide that the electric field due to an infinite plane is sigma over 2 epsilon naught. So for plane 1, that's going to be sigma over epsilon naught. And because they're both pointed to the right, they're both positive. Remember when we talk about vectors, it's important to switch our hats from voltage to electric fields here. When we talk about vectors, we assign the positives and negatives based on the direction the vectors are pointed. We assign the positives and negatives based on the way the vectors are pointed. When we did voltage, we have to actually put the positives and negatives because they're scalars. Scalars put positives and negatives into your problem. Vectors assign positives and negatives based on which way they're pointed. Both of these are pointed to the right, which means these vectors are going to help each other. They're going to add up. So they're both positive. So E1 is going to be sigma over 2 epsilon naught. E2 is going to be sigma over 2 epsilon naught. They have the same Q, they have the same A, therefore they have the same sigma. And if you add those two things together, you get 2 sigma over 2 epsilon naught. The 2's cancel. And we get our equation. Sigma over epsilon naught. AKA, it's twice as big as for one plane. Just multiply the one for one plane by 2, and you get the new equation. 2 planes, twice the influence. Okay. Why are we doing this? We're building towards our definition of capacitance. In physics, I'll keep reiterating this. When you take a physics class, you are literally starting from our foundational understanding of reality, and we are building blocks on that. And we're getting farther and farther and farther and more complex ideas, but they all stack on each other. And that's one of the goals whenever teaching a physics class is to show you that they're all connected. And you can kind of look back on a course and think about that and see if that's true or not. At no point do we really skip a step with the exception of I can't show you certain derivations because they require calculus. That's the only time. So, we remind ourselves, to continue our derivation, we remind ourselves that the electric field equals voltage over D, or if you'd like to rearrange that, we've seen this before, that the change in voltage, and I believe there should be a negative sign here, equals negative E times D. If you have a constant electric field, it's really nice if you're moving in the same direction. We have a constant electric field, hence why these parallel plates are so useful. So the change in voltage across these is going to be E times D. Well, we just calculated E. So, surprise, we're going to plug that in. D in this case will be the distance between the plates. So ta-da, look, it's the same equation I just said, V equals ED. And again, we make it positive here because we say it's from the negative electrode. If we did it the other way around, I should have a negative sign in front. So V equals E times D. And let me peek ahead on whether or not I should plug this in. No, we'll keep going. We'll keep going. I won't write it to where there. So V equals E times E, so we're going to plug in E in just a little bit. So there's just kind of shows you that the voltage is changing linearly. So it's changing kind of steadily. The voltage changes. All this picture is showing you, the electric field is constant. The electric field is the same everywhere. The electric field is constant, but as you move, as D changes, V changes. If V equals E times D, and this is a constant, well, as I move, as my distance increases, so does my voltage. As my distance increases, so does my voltage. You can see here the voltage goes up as you move from one to the other because the distance is changing there. So V equals E times D. E is a constant. D is changing. All right. So, to help you all think about this, two plates of a parallel plate capacitor are separated by a distance D. This is how far apart they are from each other. And they're charged so that the electric field between the plates is E. E naught, not meaning it's a constant. If the distance between the plates is doubled without changing the amount of charge in the plates, what is the new value of the electric field between the plates? So I'll draw a picture of this. We have our initial situation, and we double the distance. What happens to the electric field? My hint to you, what equation did we come up for electric field due to a parallel plate capacitor? I expect this problem to trip up a few people, but there's a reason I'm asking it. It's to make a point. So what happens to my electric field? If my electric field here is E naught, and we call this one E1, what does E1 equal in terms of E naught? Is it half of E naught? Is it the same as E naught? Is it 2 times E naught, or is it 4 times E naught? My hint to you is what was the equation that we wrote down for the electric field due to two infinite planes, aka a capacitor? The last quicker question we did, what was that electric field equation? Yep, and as expected, this is definitely tripping people up. I gave this problem on purpose to make a point. All right, we'll go till 2:05, so I'll give 10 more seconds. 5, 4, 3, 2, 1. All right. I'm not going to even show the answers. I'm going to go ahead and solve it, and then I'll show you all what everyone responded with. So what is the equation for the electric field due to two infinite planes? Well, we found in our previous problem, it is sigma over epsilon naught. Do you all see distance anywhere in this equation? So guess what? If we double distance, so what? If we double distance, nothing in this equation changes. So if nothing in this equation changes, my field doesn't change. And if my field doesn't change, my answer is B. The field does not change. Again, I expect, remember, don't worry if you missed it. It's not going to really affect your grade. You get 75% of the points for just participating. At the end of the semester, I'll grade the questions at a 75%. So whenever you all miss a question, it has 0. As long as you answered every question in the quarter, you get 100% for the clicker questions. Anything extra you get is extra. So, you may be like, but I just saw distance in the equations before. You did. Voltage equals E times D. So if my voltage is initially V naught, and we use our equation V equals E times D, and I double the distance, so D becomes double the distance, then yes, my new voltage is twice what I had before. But the electric field is the same. So that's where you just have to be careful with these kind of problems. Again, I honestly just gave this problem a group point. Electric field is constant in a capacitor as long as the charge on the capacitor stays the same. That is the only variable you can fundamentally change in here easily. Technically, I guess you could like rip one of these things in half, but that's just like a nightmare to do. It's not going to happen. So really the only variable you can change on this to change the field is how much charge you have stored on it. That's the only thing you can change. All right. So, just again, proving the point, the electric field inside a capacitor has 0 dependence upon distance. I'll give you a hint, a question like that will 100% show up on the test. So that's a very important concept to remember. The electric field due to an infinite plane, or 2 infinite planes, or 5 infinite planes, or 15 infinite planes, does not depend on distance at all. So if you double distance, who cares? If you half the distance, who cares? All right, so let's go ahead and get to what capacitance is. Let's start to, get to some of the things. So this is literally just plugging in V equals ED. Well, we said that E is sigma over epsilon naught. Sigma is Q over A. So it's just plugging things in as we go. I'm actually going to write this. Yeah. To just make it a bit more clear, I'll do it on the previous slide. I'll write out what is already in writing there just so you can see each step as I do it, and it's not all presented to you in one big blob. So V equals E times D. Well, E equals sigma over epsilon naught. We still have D. Sigma is Q over A. Epsilon naught times D. And so we get that equation that was on that last slide. This is literally the exact same thing that was just written. I just did it step by step just so it wasn't overwhelming. We just took, again, we built up our knowledge of what we understood before, and it's QD over A epsilon naught. I'll go back to the much nicer one that's an easier, hopefully easier to read writing. Voltage equals E times D equals sigma D over epsilon naught. So it's the exact same thing I just wrote. So that's the voltage in a capacitor. And this is where we introduce the idea of something called capacitance. We define capacitance as how much charge can I store on this thing per the amount of voltage I apply. If I hook it to a big battery, I expect to be able to store more charge. If I hook it to a small battery, less charge. So let's kind of normalize that voltage. Let's come up with this idea of capacitance. And if you think of the word capacitance, it sounds a heck of a lot like the word capacity, how much it can store. Now that's going to be dependent upon voltage, so we divide that out. So we take our voltage here, we just punt that into this equation. The Q's will cancel. Bam, there they go. Keep flip change. Anytime you divide by a fraction, just whoop, flip everything on the bottom to the top. So that A and that epsilon naught go on top, that D goes on the bottom. Ta-da, you just derived capacitance. Capacitance, and there's going to be a nicer slide on the next one. The next slide's got this equation nicely. This energy I put here now, we're going to talk about that more in later slides. We can talk about how much energy is stored in a capacitor. Again, we'll talk about that in a later slide. The derivation technically requires calculus. Again, you're going to keep seeing. This is why calculus is important. It lets us derive and discover things, just like algebra is useful. Calculus lets us do things that we couldn't do without. So we're going to get to those equations on the bottom. I'll linger here for a couple more seconds, but we're going to have some nicer slides that kind of represent this, and we'll focus on each of these individually. For now, the major thing I want you to know is that capacitance is how much charge you can store in a capacitor per amount of voltage you put on it. And capacitance has two equations. Q over V, how much charge you have divided by how much voltage is applied to it, and epsilon naught A over D. Those are both two equations that are equivalent to each other. That's how they're derived. And bam, here it is again. As I just said, two equations. We're going to use both of those. Capacitance is how much charge you can store per volt applied. The unit is the farad, as always, named after the person that kind of came up with it. So anytime you hear the word microfarad, millifarad, that is a capacitor. 1 farad, and this continues to be a theme in this class, 1 farad is a very big capacitor. That can store a heck of a lot of charge. We've said that 1 coulomb is a lot, 1 farad is a lot. When we get to current, we're going to learn that 1 amp is a lot. So for whatever, because we're working with charges, which are little itty bitty things, when we just get to kind of normal numbers, whole numbers, they end up being a big effect. Yeah.
You give a study guide before the exam?
I go through and I do the like note card thing with all the equations that are on it, and then honestly the study guide is kind of go through the problem set problems, kind of review those, and the quiz problems that we did.
So I saw Gauss's law, and I was wondering if there's any other laws we have to remember.
No, that's even Gauss's law. The only thing you need to know for that is that whole flux equation. No, when I do that note card thing, it'll be, hey, here are all the equations you need to know. And basically every equation you've had to use in a problem set, those are the equations you need to know. Nothing extra. When I made the test, there's still technically 3 problems I need to make. As I'm making it, I literally have the test on one side, and I have either the problem set or my slides on the other side. So when I'm making the numerical solving problems, I have the problem set there. When I have the conceptual questions, I'm looking at the clicker questions I've given you all. And I'm directly basing it on those. Yeah. Try to make it as aligned as possible. Okay, so we have our equation. I want to point out 2 things. I want to point out one thing here. One of these is purely geometric. Geometric meaning the capacitance is purely based on how much area you have and how far apart they are. So it's purely it's literally how did you build it? How big are your plates? How far apart are they? Great, you can get capacitance. You can also get capacitance if you know the charge and the voltage. So if I ever give you the dimensions of some, if I say, wow, I have two infinite planes and they're this by this and they're this far apart, bam, capacitance is purely geometric. The bigger the plate, I mean, just let's think through this real quick. The bigger the plate, the more area I have, the more charge I can fit on it. The bigger the bucket, the more water you can fit in it. Fairly straightforward. The shorter the distance, the stronger those charges. I told you all the electric field doesn't change, but when we actually get to kind of charging these things, this is kind of a helpful way. When we think of these planes, what's actually keeping these charges locked on there? Well, they are the charges on both sides, and so as they get kind of closer, it makes it easier to kind of hold them. I won't get into that too much because I don't want you all to mix up that whole electric field doesn't depend upon distance. But the equation, the area one at least is very easy to explain. So, two plates of a parallel plate capacitor are separated by a distance d, and they're charged so that their potential difference across them is V naught, which just means it's a constant, it's some number. If the distance between the two plates is doubled, if I double the distance between those two plates, what is the new value of the potential difference? And you all could have answered this before I gave you all that nonsense. So honestly, think of that electric field problem we just did. So I gave you all a bunch of this. I probably should have put this one after the electric field one, because now you're probably more likely to get it wrong. Think of, my hint to you, what is the relationship? We said that electric field doesn't change, but what's the relationship between electric field and voltage? What's the relationship between electric field and voltage? And distance. So, that should hopefully help you out. I kind of gave you all this answer by I literally wrote down the answer to this in the last clicker question. So, that's okay. If you missed it, again, I kind of did it as an aside thing, but if you remember it, it'll be real handy. So here, we're not asking for what happens to the electric potential. We're asking what happens to the voltage. And this, again, just proving that how they behave when you change some variables. Does the voltage half? Does the voltage double? And so, again, I just gave you all a bunch of information about capacitance, and unfortunately this question doesn't have to do with it. Don't worry, we'll have some clicker questions about capacitance. Give you all till 1:15. 5, 4, 3, 2, 1. So as the hint I gave you said, we're going to consider V equals E times D. And remember we said that the electric field, the initial one, so we'll draw our beautiful picture again. I'm basically going to draw almost identical what I drew the first time. There's my electric field, and we said if we double the distance, the electric field stays the same. So E is a constant. So we have V1 equals E naught times D. And then over here on the side, we have V2 equals E naught. But instead of having D, I have 2D, which means I have 2 times the original voltage. If the original voltage is this, E naught times D, therefore this is 2 times V1. Voltage doubles if you keep the charge the same. Again, I introduced all stuff in capacitance. Electric field's constant, voltage will change. Electric field's constant, voltage will change. I don't want to linger too much on that. Let's go ahead and start doing some capacitance stuff. Ooh, nice workout. All right, on to capacitance. Remember I told you that capacitance is purely a geometric quality. Literally, how do you build it? How big is the area? How big is the distance between them? So what will happen to the capacitance if we half the distance between the plates? So D becomes half of what it was before, and we double their area. What will happen to my capacitance? Will I be able to store the same amount of charge per unit voltage? Will I store half the amount of charge per unit voltage? Will I double the amount of charge I can store per unit voltage? Or will I quadruple the amount of charge I can store per unit voltage? I keep using the word charge per unit voltage because that's also a definition of capacitance. So, what will happen to my capacitance? What will happen to my ability to store charge? Basically, will it go down, up, or really up? Horses. Ooh, I'm seeing some. And there, for good or for bad, y'all, there will be some problems like this on the test where I say, what happens if I double this? What happens if I half this? So please go back and look at previous problems we did with these as you're thinking of studying. There is going to be problems like this. And you're going to see I kind of do them, I'm going to try to enforce how I do these problems. We write down the original, we see what changes, we put, I'll explain it as I'm solving it here. All right, we're going to go to 125. So 4, 3, 2, 1. So I'll remind you all how we're going to solve this before I give you the answer. So whenever we're doing these ratio problems, which will show up on the test, how do we solve this? We first write our original. What is our original capacitance? You could call it C1, you can call it C0. Let's just do C1. What equation has area and distance in it? Capacitance 1 equals, that's the equation. So if you want, you can put like an area 1, a distance 1. Great. My capacitance, my OG, my original capacitance is epsilon naught times area over distance. So how do I get my new capacitance? Well, when you're doing these, what changed in my problem? I halved the distance and I doubled the surface area. So whatever it says in the problem, we need to do that to those variables. Epsilon naught is a constant. You never change epsilon naught. So bam, epsilon naught's the same. Did anything happen to area? Says in our problem, we doubled the surface area. So how do I double it? I put a 2 in front of it. It's twice as big now. Okay, my area is twice as big, so put a 2 in front of it. Over, what happened to my distance? My distance halved. So I put a half in front of it. Okay, now we got a whole bunch of numbers and stuff. Once you get to this step, pull all your numbers to the front. Pull all your numbers to the front. So I'm going to pull that 2 to the front. I'm going to pull that, I'll write it the way it's written here. 1 over 1/2. That 1/2's in the bottom, so it needs to stay there. So I'm just pulling it to the front. It looked kind of ugly, but just want to make that more clear that I just pulled that to the front. And I get epsilon naught A over D. And here's why we pulled those to the front. This is C1. So whatever that number is in the front, that's what happens to it. We just need to, what's 2 times 1 over 1/2? Well, remember, dividing by a fraction, keep flip change. 2 goes up top, so we get 2 times 2 times C1. Because C1 is everything that was left over, which is 4 times C1. So when you're doing these ratio problems, this is all, you write the equation, then you write it a second time, but you just put what changed. Whatever variable doubled, put a 2 in front of it. Whatever variable tripled, put a 3 in front of it. Whatever variable halved, put a half in front of it. And you just have to be careful when you have those squareds, because when you do have those, whatever happens to it has to be squared. Look back to there was some problems we did with electric field where that comes into play, and forces where that comes into play. So, quadruples. And again, if you felt like that was a little tricky, you were in good company. So, these are important problems to be able to do, though. I'm going to keep asking these ratio problems. Again, don't worry if you miss it. It's not going to die. Yeah? Yeah. So yes, that is a great example of capacitance. If you imagine a cloud as an infinite plane, and you imagine the ground as an infinite plane, that cloud builds up with a bunch of charge, and eventually it becomes so strong that you get something, it actually tries to jump across it. You can have capacitors. You do not want charge to jump across these plates, because if they do, that means your capacitor broke. That's when capacitors will explode. If you charge them too much, eventually you get something called dielectric breakdown, which just means that that insulator between them, which was supposed to keep them separated, no longer kept them separated. And it jumped the gap, and that's what lightning is doing, is it's jumping the gap. Yeah?
Is a high energy lightning bolt more due to the distance, like the lengthy distance between like the sky and the earth, or is it?
It will, you're going to probably have a bigger lightning bolt because it's got more air to go through. You're going to be able to build up more charge if those things are farther apart. I believe. I'd have to think about that a little bit more. It's a good question, though. All right, let's see. So we've introduced the idea of capacitance. We've done some kind of ratio problems, but we haven't talked about how they become charged. So how do you charge them? And this is where we start getting into circuits. Shock and awe, you put a battery on it, or you plug it into the wall. So we charge them with a battery. And now we get to see that voltage. So how did we get a voltage? We saw the equation before that C equals Q over V. Where did the V come from? It's the battery. Whatever the battery voltage is we're going to find is going to be the whatever the battery's voltage is will be the capacitor's voltage. They'll be the same. And this is going to be a trend. We're starting to dip our toes into circuits now. Remember I told you all, every time I talk about voltage, it's a difference. So even when I talk about batteries, and I say, let's imagine that this is a AA battery, so it's a 1.5 volt battery. That means one side of it, the positive end, is 1.5 volts, and the other side is 0 volts. Or make up any numbers you want, just make certain they subtract to 1.5. I could have chosen 10 and 8.5. I could have chosen 100 and 98.5. Long story short, this end's 1.5, this end's 0. If this end is 1.5, everywhere on this wire, we're going to learn that these wires kind of hold that voltage. Everywhere on this wire is 1.5. This is 1.5. This is 1.5. Everywhere on this other wire is going to be 0. This is 0. This is 0. And so if this end is 0 and this end is 1.5, it still subtracts to equal 1.5. So it gets the same voltage as the battery does. And we need to charge our capacitors because if you don't charge it, you just have two planes of metal. Woohoo. That doesn't do anything for us. You need to actually charge it for it to actually be useful in electricity. So, how do we charge it with a battery? And it gets the exact same voltage as the battery. That's the key point here for now that you need to know. The capacitor gets the exact same voltage as the battery. This is the important part. It gets the same one. As long as it's the only thing in the circuit, we'll eventually, as always, make things more complicated. But for now, we'll just have one battery and one capacitor. And it gets the whole voltage. It's like a single child. It gets all the attention. Once you start getting 2 or 3, it's got to get split up. So, all right. Now, we talked about energy. I mentioned it previously. These are the equations. So this first equation, I don't derive it for you all because it requires calculus. I'll just quickly show you all what we would have to do. And if any of you know calculus, we have to actually integrate over the voltage. So we got to keep adding charges. You don't need to know that integral up there unless you like calculus. We got to keep adding charges to it. And as we do so, it gets harder and harder. You can almost imagine like blowing up, balloon's not a great example. As we add charges, remember charges repel. So as we add charges to this plane, say we're adding a bunch of negatives, they're going to keep repelling. They're not going to want to keep, we have a wire. It's not going to want to keep adding negatives. At some point it gets harder and harder and harder and harder. Maybe like blowing up a bike tire is a good example. At some point it gets harder and harder to blow it up as more air is kind of pushing back on you. And so we have to integrate. An integral is literally just an addition that lets you control for changing things. So we do this integral and we add up all the charge and you get the equation down here. Again, you don't need to know the derivation, but just know that it comes up from adding charge to it, which gets harder and harder to do. And bada bing, bada boom, you get a beautiful equation down here, which says that the energy stored in a capacitor is 1/2 Q times V. Now, there's 2 other forms here, and this I can show you all very simply. How did I get 3 different forms? Well, we know that C equals Q over V. C equals Q over V. So, if C equals Q over V, if I want, I can solve for, let's just solve for Q first. Q equals CV. All I did was multiply that V over. Okay, I can take that Q, put that right there. So if Q equals CV, and U equals 1/2 Q times V, take this Q, put it in there. So 1/2 C times V times V. All I did was use that C equals Q to V, solve for Q, plug that in. 1/2 CV squared. Ta-da, I got the second one. And I could do it again and get the third one. These 3 forms basically are just, if you know the first one, and you know C equals Q over V, you can derive the other 2 on your own, or you can just have them all written down and not have to. So if you want to find the energy stored in a capacitor, and I know the charge and I know the voltage, bam, use that one. If you want to find the energy stored in a capacitor and I know C and I know V, bam, use that one. If you want to find the energy stored in a capacitor and you know Q and you know C, but just use the one that has the two that you are given. So there's the derivation for how to do one of them. The other one is just some more algebra. I'll let you all do that on your own if you would so desire. The only thing you need to do is solve for V, plug that in for V, and you'll get Q squared over C. I'm not going to spend a few seconds on it because fun thing to do on your own. But this is how much energy they store. More charge, more energy. More voltage, more energy. The lower the bigger the capacitance, we get more charge up here though, and we get, so you get the idea. The C and the V the Q and the V are pretty much easy to understand. C on the bottom here may be a bit funky, and that just comes from the derivation. All right. So, before I even start this, let's think through this. This is going to be an important concept. This will kind of close out our class. Understanding we have three variables, Q, C, and V. You can see those are the only three choices here. If I charge a capacitor, I disconnect it from the battery, I double the distance between the plates. I take those plates and I separate them. What stays constant? Charge, voltage, or capacitance? Give it a go. There's a couple different ways. You can do process of elimination to figure it out. Or I can think about it. I charge these two plates. I don't even know if I want to draw a picture. If you draw a picture, it kind of gives away some of it. I charge them, so they're connected to the battery. I disconnect it. It's disconnected from all the wires. So I just have two planes, they're not touching, and then I just double them. What's going to happen? So I can at least draw that. So it's connected to a battery. Boom. So step one, connected to a capacitor battery. That's the symbol for capacitor. It looks like what you'd expect, two infinite planes. So I charge it, I disconnect it, and then I double the distance between those. What happens? What stays constant? So these last three problems I'm going to give you all basically are the three scenarios that you can do with a capacitor and kind of just thinking through what. So what is charge? What is voltage? What is capacitance? Think of the equations. What do you think stays constant? These would be very important questions conceptually. And I will explain them both. I'll explain the answer in two different ways. So hopefully that'll help. And it's funny because this problem, part of what we're going to use here is what we did on the last clicker, or two clicker questions ago. Look at that. They all connect. All right. We'll go to 1:30, so you have 10 more seconds. 4, 5, close it out. Okay, pretty good responses here. I'm going to go with the quick kind of, the first explanation is the quickest one. When I charge it, remember what I'm doing is physically building up a bunch of charges on here. So I build up a bunch of charges. I separate it. So I take it off the battery. It's got those charges. Oh, this side should be negative. They get equal and opposite. So 3 positive, whatever. Make up a number. All right? The question to you, if I separate those plates, can that charge go anywhere? No, it's locked on there. It's literally like 2 buckets. It's like a bucket. I took the bucket and maybe I dumped it into, let's see, in this case, distance goes up. I dumped it into like another bucket. I separated them. The charge can't change. So that's the quick answer. That's the quick answer, which is charge doesn't change based on, I charged it, I disconnected it from it, I literally just took those 2 plates and separated them. Charge is the same because it couldn't go anywhere. It couldn't escape. They're stuck. They're stuck on there. They can only escape once there's a wire or literally anything touching it. So that's the quick answer. Let's prove that the other two do change. We've already proved that voltage changes. We said that E or V equals E times D. And so if that's our OG, our electric field is constant. So if we double the distance, our voltage is double. So that's 1, that's 2. So my voltage is 2 times V1. That was one of our clicker questions. Voltage doubles. Voltage doubles. Done. All right, so it's not voltage. Capacitance, we have an equation for that. Epsilon naught A over D. Who cares what's happening in the problem? If my area is not changing and my distance is, that equation tells us that capacitance is going to change. So if that's my original and my new one is this, my new capacitance is 1/2 the old one. 1/2 C1. So that one also changes. Bam. All right. Yeah.
How does wireless charging work?
We will learn about that when we get to magnetic fields. Yeah, that's a good question. A wireless charging has to do with magnetic fields, and we'll learn about that. It's called induction. All right, so let's try to do one or more of these. We'll see if we can get through another one. We got a few minutes. I'm going to move my main point slides after this. Last time I taught this, that's as far as I got. So what stays constant if I charge it, leave it connected to the battery, and then double the distance between the plates? What stays constant if I charge a capacitor? And nice thing here, rule of elimination. We've already done one of these. I'll tell you it's not the answer that we just gave, so that helps you maybe. Each one of these problems, it's going to be a different thing that will stay constant. So that's a nice little hint. I leave it connected to the battery, and I double the distance. Last time I disconnected it and did that. This time it's staying connected. What stays constant if I charge a capacitor, leave it connected to the battery, and double the distance? My hint to you is the equation we're going to use for this, the concept we're going to use for this, is one that I put a bunch of stars around because it's very important. Yeah, I think we'll have just enough time to do the last one as well. Just try to knock out these last three. It'll give us a good stopping point. In the next class, we'll kind of talk about resistors and do some actual practice problems with some numbers. All right, let's go to... We'll go to 120. What's an extra 5 seconds? And 5, 4, 3, 2, 1. All right, so let's draw our beautiful picture here. We have a battery. Boom. There's our capacitor. And then the new situation is it's still connected to a battery, but the distance between them is doubled here. So the first way I'm going to show you the answer is by the equation. Voltage of the capacitor equals voltage of battery. Done. That's the answer to that one. That's how we know it's still connected to the same battery. Who cares what happens to the capacitor? If it is connected to the battery, it gets the voltage of the battery. Done. So that's why that concept is important. That's why I mentioned that. So that's our answer. Let's prove that the other two are not the case. If I double the distance, so unfortunately to kind of prove that charge does change, we have to remember that, let's do capacitance. Same exact argument as the last one. My original capacitance is A over D. Therefore, my new one is the exact same argument. If you double the distance, you half the capacitance for the exact same reason. It does not matter what you're thinking. Capacitance is purely a geometric quality. It is purely, what is my area of my plates? What is my distance? Who cares if it's connected to a battery? Who cares if I chuck it across the room? Purely just based on what is my capacitor like. So capacitance is done. Charge, this one gets a little dicey. So this is kind of where we have to use Q over V. There's maybe a better explanation, but if capacitance changes, I kind of have to use the idea that voltage stays the same. I'll try to think through that in next class, see if I can give you a better explanation than because capacitance changes and voltage changes, or voltage is constant. But let's go ahead and move to the last one, the last 2 seconds. I kind of just gave you the answer. And process of elimination, you can guess what it is. What stays constant? I charge a capacitor, disconnect it from the battery, use the capacitor, light up a bulb, and then I chuck it across the room, but don't break it. And yes, you're starting to see it, so I'll just explain it because we got 1 minute. It's capacitance. It's a freebie. It's capacitance. Why? I didn't change the area. I didn't change the distance. Assuming I didn't destroy my capacitor, capacitance is purely a geometric property. Capacitance is purely based upon the area of my plates and the distance between them. At no point in this problem did I change those two variables. Who cares what happens to it? Who cares if it's in Denmark? Who cares if it's in this room? It doesn't matter where the capacitor is. It doesn't matter what it's connected to. It's capacitance if you don't change the area or distance. This is why I can buy a capacitor online. They can have done, it could be a used capacitor, and when I get that capacitor, it has the same capacity. You know, I buy what I get. That's valuable, right? It makes sense. It doesn't matter where it is, it doesn't matter what it's connected to, yada, yada, yada. All right. Nice work today, y'all. As always, thanks for hanging in there. Email me if you have questions. We'll finish up capacitors and resistors next time. Bam.